For those of you who may not know us, so I am an engineer at Pulumi. I work on Kubernetes focus portions of our product, and likewise Duffie does the same at VMware. And we shared a former life with some coworkers of ours here. Shout out to CoreOS. And in that time, we've seen so many good and bad things about taking Kubernetes to production. More bad than good, and we're here to tell you why we think things are starting to take a different turn for the better. So I'll turn it over to Duffie.
How's everybody doing? So I'm Duffie. I'm Maui Lion on Twitter. Feel free to follow me. I'm trying to introduce my account, so feel free to follow. I'm talking about Kubernetes pretty much all the time. In this talk, we're actually going to talk about some of the security surface of applications and how to think about them. We're going to show you some kind of cool command line tools or some tricks about things. I'm also going to give you a quick high-level overview of Kubernetes. We're going to talk a little bit about what is a container. We're going to talk about, I'm going to give you a quick 5-minute overview of what is Kubernetes, and we're going to talk a little bit about what is a container, and then we're going to talk about how you can use container orchestration, basically the form of container orchestration that Kubernetes takes, to do some things maybe that you don't, as a cluster operator, want people to do. And so we'll kind of go through those examples, and then we'll also show you how you can actually mitigate that. And so this ties into the application security story by actually showing you some of the controls that you have within Kubernetes cluster to actually mitigate some of the risks that are just inherent in Kubernetes. So this first slide just talks about all of the. I'm right in front of the speaker. So this first slide talks about basically all of the moving pieces of Kubernetes, and we're just going to talk about it as an application here. So in this slide. So I'm actually going to step on the other side of it. Go for it. So, in this slide we have all of the moving parts of a Kubernetes cluster. So when you spin up a cluster in EKS or in some of these other environments, you really don't have any idea of what's happening inside of the dotted box. It's kind of happening outside of your control. But if you're actually standing up a Kubernetes cluster in other environments, leveraging some of the open source projects like Cluster API or Kubernetes, then you actually get to see all of these pieces working together. Let's talk about what they are just really quickly, give you a high-level overview. The API server, as you can tell by all of the arrows, is basically kind of like the center of the universe within Kubernetes. This API server does exactly what you might think it might do, right? It's going to do things like validate resources that are being submitted via the API. It's going to handle things like authorization, authentication, those sorts of things. It's actually also where admission control happens, and we'll talk a little bit about that as we move down through the talk. Below the API server, we have the controller manager. This guy's job is actually to have a number of control loops that basically iterate over and over again and try to break down a higher level of abstractions, things in Kubernetes like called deployments or stateful sets down into pods or the lower level of abstractions. Then we have the scheduler, which does what the scheduling things, right? It associates work with actual nodes. And as we're talking about nodes, we can look over here on the right, see 2 kubelets and a container runtime. This is actually where all of the heavy lifting happens. When we were talking about pods, that's actually the minimal viable schedulable resource within Kubernetes. Those pods are actually realized on the kubelet, and the kubelet takes care of the life cycle of that real process running on a server somewhere. That's what the kubelet's job is. Lastly, we have etcd, which is basically a key value store that stores the state for all of the Kubernetes clusters, or all of the state within Kubernetes. That's a quick overview of all of the components. Let's talk about a flow here. So in the previous diagram we said kubectl apply pod. We're going to actually be doing that live in a demo. I want to talk about what actually happens under the covers when these things happen. The reason I think this is important is because Kubernetes itself is a distributed system and a loosely coupled one at that. Once a pod is actually created, that pod object or spec is being submitted to the API server. The API server goes through the process that we talked about before. Once it's actually allowed admission into the cluster, that pod spec is persisted into etcd, the key value store, and then the API server returns 200 OK. You've given me a resource, I've accepted it, we're done. The next thing that happens is that the scheduler, upon determining that a pod has been created but is not associated with a node, will actually take that pod object, determine where to schedule that object, and then persist back to etcd the node name field, or the selection that it makes. And again, the scheduler is now done. Doesn't do any more work than that. It basically just populates that node name field based on the predicates that are provided by that pod spec. The next thing that happens is actually the heavy lifting. We're going to start this process on a kubelet somewhere. So kubelet will actually also have a watch on the API server. It'll see that there's a new pod that's been defined, it's been associated with this node. I'm going to download that spec and start doing real work. I'm going to start those processes that are defined within those containers and run them on a server and manage the lifecycle of them. And I'm going to report back up to the API server things like status. One thing that's interesting about this slide is if we go back to the previous one, we can see that there's a controller manager in this diagram, but there's not a controller manager in this diagram. This is a loosely coupled system. I've defined a pod, which is already the lowest level abstraction. This is already the lowest level primitive, so there's nothing to break down into smaller primitives. There's no need for a controller manager. If I had specified within the pod spec a node name, if I had populated that field, I could take the scheduler out of this picture as well, because there'd be no scheduling to do. And we're going to show what this means and why this might be like a security service for Kubernetes clusters in general. That was my 5-minute Kubernetes talk. That was probably a little more than that, but it's what it is. So next I want to talk about like what is a container. How many people, actually in the room, I should have asked this already, but like how many people in the room are already pretty familiar with Kubernetes? Right on. Well, the rest of you did that like kind of a crash course override of what it is. How many people in the room are familiar with containers? How many of those people can tell me what a container is in reference to like a Linux kernel or a process? We're about to expand your horizons. When you log into any Linux host and you type ls-al/pid or /proc, the proc file system, and then some pid, and then the directory ns, you will actually see a mapping that represents what a container is. In general, all of those things within that mapping, and we'll show this when we do the demo part, will agree on the particular namespaces that they're associated with it. But effectively, every process within the Linux kernel has the primitives necessary to define isolation on a process level. Right? All containerization is basically just making use of all of those primitives to provide a different mount file system, or a different container file system that's shipped with your container, or a different network namespace associated with just that one pod, or a different PID namespace, so that when you're inside the container, the only process IDs you see are the ones that are associated with that particular process. Right? This is just process isolation. And this is the kind of the aha moment when we think about like what the difference between virtualization and containerization is. Right? Containerization is process isolation. If you start a process within a container and that process dies, the container dies. If you start a process within a VM and that process dies, the VM doesn't care. It's going to keep going in perpetuity. This is the key difference between the two when we think about it. We're also going to talk a little bit about Docker and Docker. How many people here know what Docker and Docker is? A few more of them than I expected. How many of you think that Docker and Docker is exposing the underlying Docker socket on a container host to the container? One. How many think it's actually exposing enough privilege to the container to create container primitives directly? Nobody here. All right, we're moving on. All right, I get it. Okay. So this is actually a description of what a container is when we think about like all of the different namespaces. We talked about what they mean. A container is a mount file system. This represents the actual Docker image, that file system that ships as part of your Docker image. A container file system, any shared mounts, like if you actually have like persistent volumes or anything else like that, those sorts of things are actually associated with a particular container. All of these things are Linux kernel primitives that are together represent what a running container might be. And you can do things like limit things like memory, CPU, I/O. You can do things like create different network namespaces. You can share all of these things between containers within a particular pod inside of Kubernetes. And then there's also a set of constraints that you can apply. Like you can define Linux kernel capabilities, like whether you want to be able to provide to the container the ability to manipulate the network of that container. There's quite a lot of constraints that we can define. And we're going to talk about like what that surface looks like within Kubernetes as well. So that was the quick crash course of Kubernetes and containers. Now I'm going to show you some kind of like maybe not so great things. I'm creeping in front of the stand, like right in front of the speaker, so that I don't feel it. All right.
You are literally
You are, yeah. Or EM shield. Yeah. So this is a one-liner that actually allows any authenticated user, without, in the absence of admission control, to take control of the underlying node. And this is leveraging the kubekettle command line tool that ships with Kubernetes, and what it does, effectively, is it will actually just deploy an Alpine Linux image, and it will use NSEnter to mount the underlying node's PID namespace and file system, and then we'll actually use NSEnter inside of this container to basically take over the underlying node. This is possible for any authenticated user inside of a Kubernetes cluster within the absence of admission control. So let's show that off a little bit. What I'm going to do is I'm going to show you the actual manifest I'm going to use this, and basically it's just like that one-liner, but I've actually just created a container that will actually allow me to schedule this directly on a host. And just like we were talking about before, with the direct scheduling attack, if I populate the node name, I don't have to have a scheduler running. I can actually pick any node that's registered with the cluster to target with this particular attack. So I'm going to go ahead and apply that manifest. And I'm going to exec into that container and look at the result of NSEnter. NSEnter is a tool that can be used to enter into any of the namespaces associated with any given container. It's a great tool that really exposes a lot of capability for interacting with all of those primitives that make up an actual container. I've used NSEnter to solve the mystery of how a pod is actually configured. Like if I wanted to understand what ports are actually going to be bound to a specific pod, I might want to actually see the result of SS-LN within a container and see what actual process is actually bound. So in this case, what I'm going to do is jump into an NSX pod or an Nginx pod, and I'm going to look at what ports it's bound into. And so in this case, the NSEnter command basically allows me to enter the network namespace of that running container inside of my local machine here. Basically only by identifying the process ID or PID ID that is working on this particular node. Once I enter in, I can do things like SS-LN, which is kind of like the equivalent of netstat-RN, and I can see that this particular container is binding on port 80. So that explains my mystery, right? It wasn't working because it wasn't designed to work the way I expected. I can also mount it to the file system and look at the configuration of these things. Now what's interesting about this is that I can do these particular things even if the container itself doesn't have a bash or doesn't have a shell located. Talk about what this is. So this is actually that mapping that we were talking about before. And so in this particular container, we can see the mapping between the C group, the IPC namespace, mount, network, PID, all of those things, and a particular number. These numbers are specific only to this pod or this container. If you SSH into a host and you looked at all of the rest of the processes, you might see that they all agree on this number. But what else can we do here? As we talked about Linux's namespacing all of things all the time, we can also use NSEnter to take over the host without host path. We haven't talked about host path, but we did get possible. So in this command, I'm actually going to use NSEnter again. I'm going to enter all of the namespaces associated with PID 1. Now what's neat about this is that basically what this allows me to do is get root on the underlying host. This one-liner allows me to actually completely take over the underlying host. Right? I can do IP adder. I can see the underlying host, I can do pretty much anything inside of the space. I have complete ownership over the underlying host. And this is possible in any Kubernetes cluster in the absence of mission control. So that's what an authenticated user can do inside of Kubernetes. Without, in the absence of permission control, they can do pretty much anything to the underlying host. How do we fix it? How do we actually stop that from happening? The only surface that we have to actually control this is admission control. And this gives us the ability to validate or mutate resources as they're defined inside of the API server. So in this case, I'm actually going to show off pod security policies and how those things can actually allow us to limit the scope of this particular type of attack. Pod security policies act as an admission control for your Kubernetes clusters. And they allow you to limit things, constrain things in a reasonable way. Pod security policies give you the ability to define things like within the particular pod spec, within that container that we created. You'll notice that I set the privilege flag. Well, I can set a pod security policy globally within the cluster that says nobody can define privilege flags. And if I needed more than that, then I can actually allow only those pods within a particular namespace to have that capability, but deny everybody else that particular capability. Same thing with the underlying host file system or host network or capabilities, all of those things. I can constrain all of those with pod security policies and apply them cluster-wide. Now the ordering of pod security policies is a little tough to wrap your brain around, and the UX I think could use improvement. But generally what happens is that the ordering of pod security policy application will be validating before mutating, which means that if you have defined multiple pod security policies within the scope of a cluster, whatever entity it is that's creating that pod, if they have access to multiple pod security policies, the first one that actually allows admittance without mutating the object will win, and only that pod security policy will apply. They're not additive, they don't accumulate or aggregate. It's just the first policy that applies that doesn't change the object will win. And if no validating policy applies, then it will go through the mutating ones. And again, even a mutating one, only the first mutating policy will actually affect the pod, because at that point it has been accepted. Pod security policies are tough to work with because they actually tie into RBAC. We have to think about the entity that will be creating the pod and associate pod security policies with that entity. Within Kubernetes, we talked about the controller manager. The controller manager is responsible for running things like the deployment controller, replica set controller, and those sorts of things. Those entities are responsible sometimes for creating pods directly. And we have to associate the permissions to those pod security policies that we want to apply to them, to those specific controllers, or to groups of users. So let's do all of this with Pulumi.
Thank you, Duffie. So as Duffie pretty much showcased, this is pretty ripe for picking, right? If you're looking to attack a Kubernetes cluster without having default PSPs in place, pod security policies, you're pretty much out of luck. So the beauty of that is that in every single provider, what essentially happens, whether I'm running on Azure, whether I'm running on EKS, or if I'm running on GKE, they all come baked in with their own pod security policies, and most of them are pretty wide open. So they allow a blanket kind of policy that anything goes. That is not something you want to roll with out of the gates. So the good thing about managed clusters like EKS and GKE and AKS is that they give you a cluster, but that is a vanilla cluster. You cannot actually use that, right? Not in production. So the cool thing about Pulumi is because we support many SDKs across all of our platforms, I've literally defined 3 clusters in 3 lines. That is pretty powerful. If I want to actually go into the actual clouds, I can go and inspect that based on our SDKs, like on the column on the right, here's my EKS cluster. I define my VPC that it's going to be deployed into. I deploy some roles. I set the properties of the cluster itself, the version of Kubernetes, and then I map in some roles if I want to actually take over as a different user. When I deploy this, what actually is given to me is 3 different kubeconfigs. One for EKS, one for AKS, and one for GKE. I also deployed a kind cluster. It's a Kubernetes and Docker cluster, and that is just local. So essentially, all you need to work with the Kubernetes cluster in Pulumi is a kubeconfig file. We wrap a provider around that, and in Pulumi, that is the object that you work with. So this is pretty neat. I don't want to bore you with the details of setting a cluster up, but this runs and you get a couple of clusters. If I switch terminals here, I'm now going to deploy something into that. So because we have all these SDKs available, and because each kubeconfig is wrapped up in what we call a provider, you can now simply put this in a for loop. Hey, look, we actually have a real for loop. And in that for loop, we can do a couple of things. We can define our own default cloud security policies out of the gates that replaces all of the blanket allow that all these providers put in, and then replace that with something more coherent that actually makes sense. Not to mention deploy a real application into that. So this just kind of shows off how I can deploy Nginx with this load balancer into all of these different clusters. And so if I run an update, which I've already done for all of us, I get all this output, and I can literally go to Nginx on Azure, I can go to Nginx on EKS, I can go to Nginx on GKE, I can go to Nginx on my Kind cluster. But wait, I'm getting yelled at because I don't have the authority here as an anonymous user to do this. Why? Because my default cloud security policies have revoked all of those open wide privileges. So the neat thing about that is that we can not only set our own defaults, we can now showcase that we've provisioned all of our infrastructure, IAM, all the networking, the cluster itself, and then once the cluster is up, we can hook into that cluster and deploy anything else that we needed to have. So in this case, we have cloud security policies. Pulumi, by default, our SDKs do not manage cloud security policies, but we have this notion of what's called a dynamic provider, something that I can create a CRUD interface on, and I can manipulate to my heart's content. So in this, I've gone in and I've said, look, for each of these providers, some of them come with defaults that I cannot strip away. GKE, for example, if I were to remove all these cloud security policies from GKE, all of their stuff would break. Likewise, in a very kind of wonky manner, AKS comes with its own cloud security policy, but if you try to delete this root privileged cloud security policy, they have an add-on manager that will add it right back in seconds later. So what do? We have to at least scope it to our capabilities to make sure we have least privilege, and that we have some control of what comes in after the fact. Because again, the Lego blocks that we were given as the provider, they stop once that cluster is up. So it's on us to take the ball from there. So I decided to say, these are the required cloud security policies. And if you've worked with Kubernetes, I decided I'm going to create my own cloud security policy. I'm going to create my own demo privileged cloud security policy and my own restricted policy. But they're each going to be gated to different groups within Kubernetes. In this case, only the service accounts and the kube system namespace. So what does that look like? So if I go ahead and go into Pulumi, one of the neat things is the code is the state. So just like I deployed the Nginx app, if I were to comment that out here, that code is no longer live. And, take that on here. And if I were to rerun an update, what will happen is that because I removed the code, that deployment will go away. So you have a much easier way to work with the infrastructure, with the state that belongs to it, and this feels more intuitive to what we all want to work with.
You can iterate over these things rapidly, right? You're not in a situation where you have to define it all up front. You can just continue to iterate until you get it right.
Right, and so the cool thing is, you can do that on so if you're testing, let's say you want to do a testing across all these Kubernetes clusters, you can visualize what that would be like. And again, the code is the desired state. So that's going to go off and delete, and all the deployments are gone. Now, to talk to what Duffie was really getting to is, by default, we don't have the greatest cloud security policies, so we bake in our own. I created this cluster as the Mike Pulumi user in AWS, and by default, whoever provisions the cluster gets super root on all of this. So the super root can do whatever they want. Now, to show that, because the provider is just a kubeconfig file, I'm going to show what it takes to deploy a root privilege pod and the Docker and Docker pod that Duffie was talking to here, and show that the super root user can in fact deploy this as we expect. So that'll go off and deploy in about 15-20 seconds. And as we expect, because I am the super root user, all all of these pods will come up. And again, I'm leveraging my kubeconfig file that I created as super root. And that's just defined as the provider. And it's just a property and how you deploy the actual pods, or the deployments for that matter. So, as you see, the pod comes up as we expect. I am super root. Let's go ahead and blow that away and try that as a different user who's scoped to a more finer grained RBAC and who's not allowed to do this because they're forced to a restricted pod security policy. So I'm just going to blow that away real quick just to kind of show you a clean slate. Give that a couple seconds. But the cool thing about that is because we can just mix and match all of this, because in Kubernetes everything is a kubeconfig file, that gives you so much flexibility about how you manipulate, how you manage, and how you actually work with the clusters. And again, because we can hook into the cluster after it's up, that gives us the ability to actually set our standards, to set all our best practices, to limit actual capabilities, or to even set proper defaults that we may need. So that'll go off and delete the pods from the super root user, and that'll be done in just a second. And I'm going to go ahead and set this up for the next user who's finally scoped. So I created an additional user called BetterMike, because BetterMike knows better than to run in a privileged setting. And BetterMike is actually scoped with IAM and EKS to be only using this finer scoped rules here. They can only create pods deployments, replicate sets, and PVCs within the default namespace. Anything else beyond that, they're going to get yelled at. So if I go ahead and save this, and I run it as my BetterMike provider, which is my kubeconfig file that the BetterMike has, I will get Pulumi to show me a little bit more different output this time around. That shows that we can not only bake in our proper defaults, and then on top of that, leverage RBAC to tell us that we are not allowed to be doing these things. So I'll give it about 10 more seconds. And shortly enough, we should get a warning. There we go. And it says, sorry, we cannot run these containers because the BetterMike user is not allowed to run a privileged container. They're not allowed to use the host file system. And that by itself is miles ahead of what we would ever have the capability of doing with any other tool. So with that, let me switch back to the slides. So that pretty much does it on our end. If you have any more questions, there's our QR code. Just point your camera at it. It'll show you the link to all of our slides, to all of the repos, and look for us after if you have any questions. Thanks.
Both companies are vibrant, so if you're interested in working in this space, you can meet anybody at this table right over here, or Mike or Joe here at the top. Thank you very much.